multi-class classification with logistic regression. So last time we were doing logistic regression for binary, right? Does this person have diabetes or not? And that was done by using a bunch of like the body mass index and other kinds of predictors. Now, but then it's the natural question that you would have is, what do you do if you have multiple classes? What do you do if it's not binary? For binary, what were we doing? We were just saying that there's like either 1 or 0. So you use this thing called sigmoid function, where it gets close to 1 and 0 on the other, and you kind of make a multi-dimensional version of this so that if you have just two classes, you end up with a surface which becomes 1 on one side and 0 on the other side. And there's this boundary, decision boundary, where the probability, this gives you the probability. The probability is exactly 0.5. That was like the way we did the binary classification. But how do you do the case where you have multiple class? Right. So some ideas involve just using binary classification many times. Okay? So one way would be 1 versus 1, which means you just take these two groups and figure out the best boundary for that, right? Which is like that, right? And then you do these two, which will be like this one. And then these two will be like that. And then at some point, if you want to know which class something belongs to, you just apply those 3 boundaries and see which one's the most likely one. Right? So that's one way to do it. That looks a bit messy, so we delete those. But then you could also do 1 versus rest. So just use everything, but say you make a decision boundary that takes this, distinguishes this group away from the other two. Okay? And you can also distinguish this from the other two, so you have this decision boundary. This from the other two, so you have this decision boundary. And that might be another possibility. Right? So these are very simple ideas. Scikit-learn has packages that will do these for you, so you don't have to actually spend time coding these things. But I want to talk about a wholly new approach today, which is called multinomial. So what is multinomial? So multinomial does the following. You recall the multiple linear regression. Which was, you have your predictor y hat as beta 1x1, beta 2x2, beta nxn plus, let's say, beta 0. So you have n predictors, or we also talk about these as features, right? You have n features, and it gives you the prediction about the value of y, right? Now, same problem occurs when you try to use multiple linear regression for classification, which is that when we classify things, we want to talk about the probability, and it's either 0 or 1. It's this one or that, this or that. That's the idea that we have. And a linear function doesn't have an upper bound, right? It goes up and up, right? So you end up with a situation where the values are quite, like the things that this is trying to approximate doesn't really align with the data set that you have, because data sets are either 0 or 1. Okay? So this is not a good idea. And one of the ideas that we had for logistic regression was to feed it into this sigmoid function. Just like that, right? So this goes in here, and because this function as a function of x, if you just drew the graph of this has the graph. It's also called logistic function. The logistic function has this graph that smoothly goes from 0 to 1, and therefore that allows you to kind of squash this value to something that's between 0 and 1. Okay? And then we can rewrite this in the following way. We can rewrite it as, you can multiply e to the y hat top and bottom, and we can rewrite it as e to the y hat over e to the y hat minus 1. Just like that. Okay? No, it's plus 1. Okay, so you can view this the following way. You're thinking of the output, you're exponentiating it, and then you're somehow trying to normalize it so that this has a value between 0 to 1. So this is the property that if y hat is a really large value, then this gets close to 1. If y hat is a negative infinity, this gets close to 0. Right? So that's how this formula turns this into probability. And now here's a setting for actual multinomial logistic regression. So what you do is you have, I'll use alpha, beta, and gamma, because I could also use multi-indices, but that's really confusing. So I'm going to produce predictions for, so let's call these groups alpha, beta, and gamma. Okay? So the prediction for the first group is y hat alpha equals to alpha 1 x1 plus alpha 2 x2 alpha n xn plus alpha 0, and y hat beta is beta 1 x1 beta 2 x2 beta n xn plus beta 0. Y hat gamma will be gamma 1 x1 gamma 2 x2 xn plus beta, not beta 0, sorry. But this should be beta 0, this should be gamma 0. This is not y, this is gamma, it just comes down slightly.
You're writing multiple regressions for each of the classes?
That's exactly what's happening, right? You can see that I'm doing multiple linear regression for each one of them. Okay, I'm not actually. One thing that could be confusing is that if I write down multiple linear regression is two things. One idea is that you're trying to approximate the prediction by a linear function. Another idea is that you're trying to figure out the best fit beta 1 through beta 0, beta n and beta 0, by minimizing the mean squared error. But I'm not talking about that second part. We want to minimize a different thing. Okay. So what I'm doing here is I'm just writing them as linear functions. Okay. Just as if you're doing multiple regression, but these actual values, these are numbers. Alpha 1 through alpha n and alpha 0. These are numbers. x1, x2, x2, xn's are features from the data. Okay. Yeah. And the best values for alpha 1, alpha 2, alpha n, and alpha 0, and all these would be found by first transforming those values to probabilities. And here's how you transform it to probabilities. Okay. First of all, you exponentiate everything just like before. Okay, so you just take e to the y hat alpha, e to the y hat beta, e to the y hat gamma. We want the probabilities to be in proportion to these values. Okay? But then, of course, these themselves won't be probabilities, because if this is like bigger than some value like 1 or 2, then this is way bigger than 1. It can't be, right? Probabilities should be between 0 to 1. All we managed to do by exponentiating, we just managed to make these values positive. Okay, that's a start. But then another requirement for probabilities is that if you add them up, what do you have to get? You have to get 1. So what you do is you think about this additional coefficient 1 over z. Now why am I naming the constant as z rather than c? That's due to some historical reasons. The person who first thought about this way of producing probabilities is Boltzmann, and he was like the founder of the statistical mechanics. Yeah, statistical mechanics, and he called this value z something called a partition function. So, and it's actually a very important quantity in statistical mechanics because it requires a lot of computation to figure out what it is. For us, it's a very simple quantity. Because I need these to add up to 1, multiplied by z, you immediately get that z must be the sum of these exponents, right? So that, for example, the probability of, let's say you're given a let's say you have some y. So let's say you have some y from beta. Let's say this is y. Okay. So anything that's a data will come with a feature set, right? And the actual identity of which class it is. Okay. So which class it belongs to is often called label. So y, the actual value of y would be the label. The label and the feature will be what this data point is. Okay. So the probability that will be in this feature set would be calculated by doing this e to the y hat beta divided by this z. It's this divided by z, right? So you have e to the y hat a plus e to the y hat b plus e to the y hat gamma. Okay. So what does that mean? That means I don't like this. Probability that y would be in group beta would be this.
Wait, so y as an element of beta?
Yeah. For y to be classified as beta, what you do is you take the feature sets of y, plug it in here for this formula, right? And then you divide it by this, and it produces a probability. Right?
So, to understand it further,
Yeah.
we're asking if Y is a subset of B?
No, this means it's an element. This is a set symbol for being an element.
Oh,
Yeah,
okay.
yeah.
Alright.
It's not subset is this.
Okay,
Yeah, okay, all right.
thanks.
Yeah. Okay, so, I mean, we in this picture, we took it from beta, so we kind of expected this value to be quite high if our multiple linear regression is successfully trained, right? And we would also, let's right over here, we would also think about the probability that y belongs to alpha would be E of y hat alpha over this z, where z is this sum, okay? Right? Yeah. And then similarly, we can also talk about the probability that y could be in gamma, which would be e to the y gamma hat over z. So once you pick any data from this group, you can put it into this machinery, calculate these values, right? And then calculate the probability like that. Now, what does that mean? That means every item will give you probability of belonging to group beta, group alpha, or group gamma. And it's going to be like, this will be close to 1, whereas these two will be close to 0. Right? Then you know that, oh, it must be group beta. Right? If, for some reason, we picked another data point and we calculated these three, and we got something close to 0 and 0 here, and then this was big, then we know that it should be from group gamma. That's the idea, right? Okay? Now, if you think about the exponential function becomes huge pretty fast, right? So what this means is that if one of these three values become bigger than the other ones, then they become very prominent in the probability. They become very close to 1. The other ones become close to 0. The only time you would have something that's close to 0.5 would be when you have two groups that give you similar values. Okay? If you have the outputs from the linear function giving you something similar, then the exponential functions from here and there will be comparable, and you're going to get something close to half and half. Okay? But in most cases, what's going to happen is that you're going to get a value pretty close to 1 for just one of the groups, and the other ones will be close to 0. That's what's called multinomial logistic regression. Okay, so I've been multinomial logistic regression, and this is the description. But then again, this is only half the description. Why? Because to train this, that means we have to find out the best values, best fit values for alpha 1, alpha 2, beta 1, beta 2, and all that, right? So how do we train it? To train, you need a goal. Okay, you need. I've been calling them target function, but that was wrong. Sorry, I should have said objective function. Okay, so there's in any machine learning algorithm that we've been doing so far, we're only doing regression and logistic regression, and then now we're moving to multinomial logistic regression. All of these have a goal, an objective function. For the linear regression, we are trying to minimize the mean square error. Okay? The difference between the predicted value and the actual value, you square them and you add them. And if you divide by n, that's called the mean square error. That was what we were trying to minimize, right? In the logistic regression, if you recall, I was talking about this function called log odds, which was negative y I ln of yi hat plus 1 minus yi ln of 1 minus yi hat. So this was our log odds. It's a bit confusing because the yi's here are the ones that are already squeezed by the sigmoid function. There's a bit of a difference here. Okay. So let's talk about what kind of objective function we should use for the multinomial. It's kind of similar to this. So this was the just basic logistic objective function called negative log odds. But for the multinomial one, what we do is we take negative of whether we use a Kronecker delta function, whether the label, let's say this is the original label and J is the predicted label, and then you take ln of the probability obtained by this procedure. So I'm calling these as probability. So the way I'm thinking about this is that oh no, I should just say delta I. Yeah. Okay. Delta I. I should put J. Okay, so here I is the ith data point, and then jth label. And what does this delta function do? Delta functions are either 1 or 0. If the ith data has label, let's call the label 0, 1, 2 for a minute. Okay? If the ith data has label 0, then delta I0 will be 1, whereas delta I1 and delta I2 will be 0. Okay, so I should put this over here. Delta ij, if ith label data point has label j, then delta ij is 1. If not, then delta ij is 0. So that's the idea.
Can we say that delta ij is a Boolean operator?
Usually people call this Kronecker delta function, but it's not really the usual Kronecker delta function, because Kronecker delta function is when I and j are equal, it's 1, and I and j are different, it's 0. I guess there's a way to write that in that form, but I just want to explain it like that. And it's really similar to this one, because here in the logistic objective function, what happens? Every point has label 0 or 1 in the regular logistic objective function, because we only do binary classification with this one, right? It's either this group or that group, okay? So in that case, if yi is has the 0th label, then this value will be 0, okay? And this value will be 1, and therefore it will give you the probability of belonging to 0th label. And this is the probability of belonging to 0th label, this is the probability of belonging to label 1, okay? If yi is 1, right, then this will be 0 and this will be 1, and this will be the probability of belonging to 1. And I've explained that, last time I explained that if yi wasn't like strictly 0 or 1, if it was some values between 0 and 1, this thing will be minimized when the yi agrees with that probability, right? I want to give us a slightly better argument than that one, but that's somewhat related to why the logistic objective function works. It gives you the best probability for each point to have the logistic function fit. Okay, and for the same reason, this does work as well. Okay. All right. So that's basically the idea. You try to minimize this function with these probabilities, and how do you actually do it? You still use the gradient descent, just as I vaguely explained here. Okay.